Hello everyone, I am Mrs. Ashwini Oak, a physics teacher from Fergusson College, Pune. In the last lecture, we had started interference. So let us see interference of light with the help of PowerPoint presentation. In the last lecture, we had started the phenomenon of interference and we had seen the constructive and destructive interference. Let us revise this once again. So when two waves traveling through the medium arrive at a point and when they overlap, if the crest of one wave overlaps with the crest of the other, or trough of one wave overlaps with the trough of the other, as you can see in this, the resultant displacement at that point is maximum, the resultant amplitude is maximum, and as the intensity of the wave is directly proportional to the square of amplitude, intensity is also maximum. This type of interference is called as constructive interference. When the waves overlap with each other, which are out of phase, that means the crest of one wave, the trough of the other, and vice versa, then the resultant displacement at that point is minimum, the resultant amplitude is minimum, and the resultant intensity is also minimum. This type of interference is called as the destructive interference. You can see constructive and destructive interference in this animation. Now let us understand the constructive and destructive interference in case of water waves. So we consider two sources, S1 and S2, which produce the waves on the surface of water. These two waves have the same amplitude, they have same wavelengths, and they are in phase with each other. That is, at any given instant of time, two waves produced by the sources S1 and S2 have equal phases. These two sources produce the waves which travel in the form of crest and troughs. Crests are denoted by continuous curves and the troughs are denoted by dotted curves. These two waves travel in the medium and they overlap with each other at different points. When the crest of one wave overlaps with the crest of the other, or the trough of one wave overlaps with trough of the other, the resultant displacement at that point is maximum, the resultant amplitude is maximum, and the constructive interference takes place at this point. All the points where the constructive interference takes place are shown by blue dots. When the crest of one wave overlaps with the trough of the other and vice versa, then resultant displacement at that point is minimum, resultant amplitude is also minimum. The destructive interference takes place at this point, and all the points which are shown by red dots are the points due to destructive interference. So this is how constructive and destructive interference takes place in case of water waves. Now let us see the point of difference between constructive and destructive interference. When the waves which are in phase overlap with each other, the constructive interference is formed. When the waves which are out of phase overlap with each other, we get the destructive interference. When constructive interference takes place, there is maximum resultant displacement at the point. In destructive interference, the resultant displacement at a point is minimum. In constructive interference, the resultant amplitude increases, and in destructive interference, the resultant amplitude decreases. As the amplitude increases, the intensity also increases in constructive interference, and therefore the energy becomes maximum when there is constructive interference, and energy becomes minimum in destructive interference. Interference had been observed in case of water waves and sound waves. It was observed for light waves in the laboratory for the first time by Thomas Young in 1801, and this was the proof for the wave nature of light. So let us understand what is interference of light. The modification in the intensity of light produced by the superposition of light waves is called interference of light. Now, when two light waves superimpose or overlap with each other, at some points the intensity of light is maximum, and at some other points the intensity of light is minimum. So there is modification in the intensity of light, and that is called as interference of light. When two light waves superimpose, at some points where the waves superimpose in phase, the intensity of light is maximum. At some other points where the waves superimpose out of phase, the intensity of light is minimum. So there is modification in the intensity of light which is produced by the superposition of light waves, and it is called as interference of light. Interference of light can be observed in our day-to-day life. Interference can be seen due to thin oil film on the surface of water. We can see the color pattern obtained due to thin oil film on the wet roads in rainy season. So this is one of the example of interference of light in our day-to-day life. Also, the bright colors of butterflies, the brilliant colors of soap bubbles are due to interference of light. So these are our day-to-day examples for the interference of light. Now, for the interference to be seen over a sustained period, what is the necessary condition? Now let us take an example of normal flashlight, or if we take a torch, when the torch is on, it emits light which consists of different wavelengths. So this light has different wavelengths, they have different frequencies, and also the waves are not in phase, or they do not have constant phase difference between them. Such a light is called as incoherent light, and the source which emits such light is called as incoherent source of light. Now let us take an example of a laser beam. When we see the laser beam, the wavelength of all the waves is same, the frequency is same, and all the waves are in phase with each other, or they have constant phase difference between them. Such a light is called as coherent light, and the source of light is called as coherent source of light. So, for the interference to be seen over sustained period, we need two coherent sources of light. Now let us understand what is the meaning of coherent sources of light. Two sources which emit light waves of the same frequency and the waves emitted by them are in phase or have a constant phase difference between them are called coherent sources of light. And two coherent sources are usually obtained from the same primary source. Thomas Young performed the experiment in the laboratory to demonstrate the phenomenon of interference of light by using two slits, and this experiment is called as Young's double slit experiment. So let us see the experimental setup of Young's double slit experiment. S is the primary source of light. the diverging rays from the source are made to fall on the convex lens. The emerging rays are parallel to each other, and alternatively, the wavefront is the plane wavefront. These parallel rays or the plane wavefronts are made to fall on opaque screen AB, which consists of two narrow slits S1 and S2. We assume that S1 and S2 are equidistant from the source S. So, the waves emitted by source S travel equal distance to reach the two slits S1 and S2. As the waves travel the same distance to reach S1 and S2, they have same paths and they are in phase when they are incident on the slits S1 and S2. So the waves which are incident on S1 and S2 are in phase, and therefore the waves which are emitted by S1 and S2 are also in phase. So when the waves from S reach S1 and S2, these two slits act as secondary sources of light, and they emit the secondary wavelets in the form of cylindrical waves in the medium. These waves travel in the form of crest and trough. The crests are shown by continuous curves and the troughs are shown by dotted curves. When the crest of the wave emitted by S1 overlaps with the crest of the wave emitted by S2, or trough of the wave emitted by S1 overlaps with the trough of the wave emitted by S2, the constructive interference takes place. That is, the resultant displacement at those points is maximum, and therefore the intensity at those points is also maximum. The points where constructive interference takes place are shown by blue dots. The line joining these blue dots meet the screen PQ at a point. This point has the maximum intensity, or this point is called as a bright point on the screen, or the region surrounding this point is the bright region on the screen. When the crest of the wave emitted by S1 overlaps with the trough of the wave emitted by S2 and vice versa, the destructive interference takes place. That means at those points, the resultant displacement is minimum and resultant intensity is also minimum. As the two sources are emitting the light waves which are of same amplitude, the resultant intensity due to destructive interference is 0. Those points are shown by red dots. The line joining these red dots meets the screen PQ at some points, and the point on the screen where this line meets is the point of minimum intensity, or it is the dark point. The region surrounding this point is the dark region. So this is how we can get different bright and dark regions obtained on the screen, which are shown here to the right of the observing screen PQ. These bright and dark regions are called as fringes, and the pattern consisting of alternate bright and dark regions is called as interference pattern. Now if we see the central line of S1 and S2 which joins all the blue dots, this point on the screen where the line meets is the bright region or bright fringe obtained on the screen, and this is called as central bright fringe of interference pattern. Then alternate dark and bright fringes are obtained on either side of central bright fringe. So this is how we get the interference pattern obtained on the screen in case of Young's double slit experiment. You can observe this with the help of this animation. So this is our primary source. The waves are made to incident on two narrow slits S1 and S2, and the waves from S1 and S2 interfere with each other and produce the pattern on the screen, which consists of central bright fringe followed by alternate dark and bright fringes on either side. Now let us obtain the positions of these fringes obtained on the screen mathematically. So we are considering the cross section of experimental setup. Here the opaque screen is shown and the waves from the primary source S are incident on two slits S1 and S2. So S1 and S2 are two narrow slits which act as two coherent sources of light, and they are the secondary sources of light, so they emit the light waves in the medium. We assume that these light waves travel along the x-axis and the screen is placed in YZ plane. But we are seeing the cross section in XY plane, and therefore the screen is along Y direction. Now we take that O is the center of the two slits S1 and S2, and it is the origin of two coordinates axes X and Y. The distance between the two narrow slits S1 and S2 is small d, and it is very small, of about 2 to 4 millimeter. The screen is placed at a distance of capital D from the two slits, and this distance capital D is about 1 meter. So the distance between the slits and the screen is very large compared to the distance between the two slits. Now, as I said, O is the center of the two slits. We consider one point on the screen, which is point O dash, which is directly in front of O, and it is also equidistant from S1 and S2. So when the waves from S reach S1 and S2, they start emitting the waves. We consider the wave emitted by S1 and traveling towards O dash, and wave emitted by S2 and also traveling towards O dash. These two waves travel equal paths to reach point O dash on the screen. So when these two waves reach point O dash, there exists no path difference between the waves. Also, there exists no phase difference between the waves. As the paths of both the waves are equal, their phases are also same, and therefore there is no path difference or phase difference when the waves from S1 and S2 arrive at point O dash. That means these two waves are in phase when they arrive at O dash. So O dash is the point due to constructive interference, and it is a bright point obtained on the screen, or we can say that the region surrounding this point is a bright region on the screen. So this is the central bright point of the interference pattern. So we have got the position of the central bright point or central bright fringe. Now let us obtain the positions of other fringes on the screen. For that, we are considering point P on the screen, which is at distance y from the central bright point. Now, when we consider the waves which are originated from S1 and S2, when they travel towards point P, they cover different paths. And therefore, when the two waves from S1 and S2 arrive at point P, there exists a path difference between the two waves. The path of the first wave is S1p, the path of the second wave is S2p. So the path difference between the two waves which are arriving at point P is also denoted by delta L, which is equal to S2p minus S1p. From the diagram, you can see that S2p is greater than S1p, and therefore the path difference is S2p minus S1p. Now let us find out this path difference between the two waves mathematically. For this, we draw perpendiculars on the screen from the two slits S1 and S2. So S1, S1 dash is the perpendicular drawn on the screen. Also, S2, S2 dash is another perpendicular drawn on the screen. So we get two right angle triangles, S1, S1 dash P and S2, S2 dash P. Now in S1, S1 dash P and S2, S2 dash P, we can find S2P square minus S1P square. So what is S2P square? It is equal to S2, S2 dash square plus S2 dash P square minus S1P square is nothing but S1, S1 dash square plus S1 dash P square. Now let us substitute the values. S2, S2 dash is nothing but D. So S2, S2 dash square is D square plus S2 dash P square is nothing but Y plus this distance D by 2 whole square minus S1, S1 dash square is again D square plus S1 dash P square is nothing but Y minus D by 2 whole square. Now let us open the square in both the brackets. So D square plus Y square plus D square by 4 plus YD minus D square plus Y square plus D square by 4 minus YD. Now if we open two brackets, then in the first bracket plus D square and second bracket if we open it is minus D square, so they get cancelled. Again plus Y square minus Y square get cancelled, plus D square by 4 minus D square by 4 gets cancelled, and from the first bracket we get YD. From the second bracket it is minus of minus YD, which is plus YD. So YD plus YD is equal to 2Y into D. So S2P square minus S1P square is 2Y into D. Let us take the factors of S2P square minus S1P square. So it is S2P minus S1P into S2P plus S1P, which is equal to 2Y into D. We have to obtain the equation for path difference, which is S2P minus S1P. So we write here S2P minus S1P is equal to the path difference delta L, which is equal to 2Y into D divided by S2P plus S1P. Now, as I said, distance capital D is very large compared to the distance small d, which is between the two slits. And as capital D is very large, this inclination theta of point P is very small, and therefore we can take S1P is approximately equal to D and S2P is also approximately equal to D, and therefore S2P plus S1P can be approximately written as 2D. So the equation for path difference delta L becomes 2Y into D divided by 2D. So 2 gets cancelled and the expression for path difference is YD upon D. So when the two waves from two slits S1 and S2 arrive at point P, they have the path difference which is equal to Y small d upon capital D, where Y is the distance of point from the central bright point, small d is the distance between the two slits, and the capital D is the distance between the slits and the screen. Now by using the expression for path difference, let us obtain the positions of bright and dark fringes on the screen. So let us see what is the condition for the constructive interference to take place at point P. So we are taking the same experimental diagram, and point P is at distance y from the central bright point. And let us obtain the condition for this point P, which is the bright point obtained on the screen, or the point P is a point due to constructive interference. Constructive interference is obtained when the crest of one wave overlaps with the crest of the other, or trough of one wave overlaps with the trough of the other. So here you can see that the crest of the two waves are overlapping with each other, or the troughs of two waves are overlapping with each other. When these two waves reach the point P on the screen, we get the constructive interference at point P. So at point P, the path difference between the two waves should be either equal to lambda, or it is equal to 2 lambda, or it is 3 lambda, or 4 lambda, and so on. When the path difference is lambda, then the two waves overlap with each other as crest overlap with crest and trough overlap with trough. Also, when the path difference is 2 lambda, again the crest or troughs overlap with each other. When path difference is 3 lambda, again the same case happens. So these are the path difference for the point P to be bright on the screen. So in general, the path difference between the two waves for the constructive interference can be written as yn into d by d. This is the expression which we have obtained in our previous slide. Yn is the distance of nth bright point from the central bright point. D is the distance between the two slits. Capital D is the distance between the slit and the screen. That should be equal to integral multiple of lambda from the previous equation. So delta L should be equal to n lambda, where n takes the values 0, plus minus 1, plus minus 2, plus minus 3, and so on. In this lecture, we have seen interference of light, Young's double slit experiment, and the position of bright and dark fringes obtained on the screen. We have not yet finished the topic. We will see the remaining things in our next lecture. Thank you.